All right, everyone, welcome back. I hope you enjoyed your long weekend. I know that is utterly meaningless at this point. You probably just got caught up on videos. So today is lecture 4, hour 4 of our 45-hour lecture series for this entire class. Some good news, apparently the university has managed to get rid of the birds, so I didn't have to bring the dog this time. I'm not quite sure what they did. Is there a monkey over my shoulder? And that's why we bring monkey sticks to the lecture centers now. All right, so that happened. Be interesting to see what happens next. Maybe we'll have a family of raccoons move in here. How logic played in with the authorities. Anyway, moving on, let's review what we did last time, which is to talk about our derivation of probability distribution for velocity. This is the formal Maxwell-Boltzmann equation. And one thing I may do on the test is ask you to identify the various pieces. In the last Friday, we talked about where 4 pi v squared comes from. That is from the Jacobian. We're actually going to, in the Friday extra hour this week, I'm going to go over a full explanation of where that comes from. Let's see, this is the normalization part from the Boltzmann equation. This part is like the business end from the Boltzmann equation. And there you go. Let's see. Last time we talked about integrating it over all possible values from 0 to infinity. We used an identity and we got the number 1, which is interpreted as a molecule is either moving or not moving, which I don't really need to do any integrals to know that. It's good that I got the number 1, which is 100% true that a molecule is moving or not moving, and that's for certain. However, I hope that there's some better utility than just that, and there is, which is what we're going to spend a lot of time on today. Today has the biggest oomph of this Maxwell-Boltzmann section, which we're doing the first 2 weeks. Okay, now what's important about this is that you understand how to do averages. Now, I know you learned how to do averages in the 2nd grade, but did you? You did. All right, what did you learn? You learned that if you had a set of, let's say, 3 numbers, let's take 1, 2, 3, make it as easy as possible, then the average would be the sum, which is 6 divided by n, the number. So that's 6 over 3, which is 2. Sure, why not? Now, let's do a little bit more advanced way of thinking about why that is. In that example I just gave, there's technically a 1/3 chance that you're going to observe a 1, a 1/3 chance you're going to observe a 2. So these are like dice in a bag and you're just pulling the dice out. And so that means you have a 1/3 chance of observing a 3. Right? And that, of course, is 2 if you just use your calculator. Or maybe you can do that in your head. All right, so that's fine and good. Now, what that implies is that you have a probability distribution that looks like this. It's a top hat. Very common. It applies to dice. 1, 2, 3. So you had a 1/3 chance of observing a 1, 2, or 3, and then this is the mathematical definition of a probability. Now, if you're a little bit more advanced, you realize that there are things called bell curves. And so let's apply a bell curve to this same problem. It maxes out at 2, and then there's a 1 and 3 evenly to the right. Perhaps the top is 0.5, and in the middle is a 0.25. And therefore, the average would be 0.25 times 1, you can see that right here, plus 0.5 times 2. And again, that's consistent with the graph. And you could have also had 0.25 times 3. Now, did you notice how the probability parts always sum to 1? That's important. If that's not correct, then you're doing it wrong. Put it in your calculator, you get the same answer too. Okay. So what I want to point out here is that when you used your elementary school math, you made an assumption. You assumed that you either had a top hat or a bell curve. Now, here's the thing. Top hat and bell curves are unbelievably common. That is not a bad assumption. So you really didn't necessarily do anything wrong. But occasionally nature throws a skewed distribution like right now. Okay, so what could happen? So here's kind of, I'm just making things up, all right, but here's the idea. So here's a new probability distribution, and let's give it like a really weird shape just because that's what happened. Here's 1, 2, and 3, in which case now the average, oh sorry everyone, there's a camera glitch, I just had to fix it. So in this case what you have is an average would be, again I'm just making up numbers, 0.25 times 1 plus 0.25 times 2. So that means I better have 0.5 chance of observing 3. And let's see, what is that? That's 0.25 plus 0.5 plus 1.5. And so that's 2.25. A little bit bigger, right? A little bit bigger than 2. Okay, so you can see, again, that you have been working under some assumptions that are not bad assumptions, but they're not always going to be true. And if you see you have a skewed distribution, you might have an average that's a little bit further to the right than you would have erstwhile expect. Okay, now one thing again that you observe from here is notice how I'm taking the observable and multiplying it by the probability and summing up over all possible observables. Okay, now when you apply that to an equation which is not discrete, and that means like 1, 2, 3, instead it's continuous, which means that you could basically have any velocity. Instead of a sum, you have an integral. And I told you this last time, but let's write it down again, because why wouldn't we? So the average value, and let's go ahead and say it's velocity, but this could be anything, so it's like y in my, I always put things in terms of an average value of an observable y. In this case, for Maxwell-Boltzmann, y is v, and you take your probability distribution, multiply by the thing you're wanting to take the average of, partial, of course, if you have a partial, you're now integrating, and then you have to integrate from a lower to upper limit where that represents the range of all limits. Okay, now heads up, when you have this on a test, I will not throw this, we're going to do average value of a gas, but I will not put that on a test because that just is, that just means you just have to memorize this. Instead, because I don't want you doing that, instead, I will throw different probability distributions at you, like patients in the hospital, cats in a house, and so you have to know how to do this correctly. Okay, so let's go ahead and do our Maxwell-Boltzmann. And so in this case here, most important is take all your constants and move them out because that way it's a lot less scary. Remember I told you that most of what we're doing here have equations that go across the board, but for the most part they're just a bunch of constants, right? That shouldn't be too horrendous. Okay, now that I've removed all the constants, when it comes to the limits, I'll make sure that you know what those are. You can look at the identities. On the exam, you'll have identities. I will sometimes give you a hint at what's correct by the identities. If you get it wrong, you will not find an identity for that expression that you wrote incorrectly. And notice that when I get rid of the constants, it really doesn't look so bad, right? I think that you handled equations that look like that. You handled equations that look like that in your calc class, right? So hopefully you're looking at this and saying, no, that's not right, because it's not. I did it to you again. Sometimes I write things down wrong to see whether you catch me. What did I do? Well, here's a hint. Here's a hint. If you find an identity for this, you're at the exam, you have been asked to do this, you wrote this down, you find an identity, and you get the number 1. Well, that's weird. 1 meter per second? That's the average value of the speed of a gas. When we remember those graphs that we had last time? Remember that gases are moving really fast? They're not moving 1 meter per second. Why'd you get 1? Because all you did was check the normalization. Why are you checking the normalization instead of calculating the average speed? Because you forgot to multiply by v, right? That's the probability distribution. Now you're doing average speed. Ching. Number one way to miss that problem is to forget that. All right. Now again, on your homeworks, I will show you how to use online integration, mathematical this and that, because why not? On exams, you'll have identities. because why not? And the identity defined, here we go. And remember that you'll have multiple identities, so you have to get good at finding these. And all you have to do is notice that X is your V. And once you've done that, you're set. And here we go, that's the identity. Remember that you don't apply limits to this. This is the answer with limits applied. We talked about that mistake last time. Okay, once you look at this thing, you realize that this is not too hard. We talked about messing up the minus sign. We talked about that in the previous lecture. You recognize that A is M over 2 kBT. And therefore, the answer is 1 over 2 M squared over 2, kBT squared. There you go. Gotcha! Did it again. Forgot the constants. Number 2 way to miss the problem. 4 pi, M, 2 pi kBT. 3/2. Okay. So, all right. Now again, on a exam situation, probably just leave it like that. If that's correct, I would accept it. If you want to simplify it, that's on you. But if you make a mistake, look, I don't mean to be a jerk, but if you simplify it and make a mistake, you gave me the wrong answer. I can't give you full credit. I mean, I can't. It's wrong. So maybe don't do that, right? Remember, we live in the day of calculators. There's no value. So I don't need you to simplify it. Back in the day when there's no calculators, this would really suck to go through that by hand. So simplifying it is awesome. But that was 50 years ago. So we don't need to do that. Now, if you did though, let me show you what you get. You would get 8 kBT over pi m to the 1/2. So square root of that. Okay. Double check the units. Maybe I have that on your homework. And there you go. All right. So, so what? Well, here, let's graph it. I don't think I'll digital this one in because it's kind of simple. So you know that Maxwell-Boltzmanns are skewed. This is kind of like a different skew than I drew up there, but anyway, it's still a skew nonetheless. And what you find, most interestingly, is that the average value is, you probably want to put it at the very top of the curve. And that, sure, I mean, I would expect you that that's a reasonable thing to do. It's not at the top of the curve. Because of the skew, the average value is slightly to the right of the top of the curve. Funny enough, it's just, I don't quite get that, but that's what mathematically this comes out to. In fact, I can calculate what the velocity is at the top of the curve. I'll do that in a minute. And in the meantime, okay, so this is, probably pretty useful in its own right. And I think I'll have you do some things with, on the homework, like calculate that the units are correct, that these are meters per second. What is the average speed of an oxygen at room temperature, yada, yada, yada. Get comfortable with units. Remember that mass needs to be in kilograms and SI. Things like that, they're important. But now here's where you can do some really crazy things. This is really nutty. Who says that you want to just calculate the average of velocity? Let me show you what you can do. Now, I hate to do this, but I'm going to do it anyway. I'm going to write over my own work. I try not to do that because I know it makes taking your notes very difficult. What you can do is, I just showed you how to calculate velocity. You can calculate the average of the square velocity. Now you can do that just by taking the probability distribution, and instead of multiplying it by v, you multiply by v squared. Okay, so then this is v to the fourth. Okay. Now again, I won't do this often. I know that this makes it hard for you to take notes, but I couldn't resist. We're a little bit behind actually. Okay. Now that you've done that, and you may be thinking, well, wait a minute, why don't I just square what I got? Well, let me show you. I mean, there's a reason I'm doing this. Okay, now what we're looking for is an identity, and we're looking for x, instead of x to the 3, you're looking for x to the 4. You're looking for the limits, make sure that the limits are correct. And this is a little bit more complicated. So notice that instead of, yeah, it's a little bit more complicated. Okay, so when you get, okay, so the normalizer is still the normalizer. Oh God, let me look at this. So you still get 3 square root of pi. Ooh, God, this is kind of awful, isn't it? Over 8. There's the constants, there's the normalizer, and then you end up with m to the 5 halves over 2 kBt. Sorry, I'm not using the board very well today. This is all in the textbook too as well. I'm obviously using the board kind of hideously today. Okay, regardless, what do you get? So again, on a test, just leave it like that. It's horrible, but whatever. Let's see. I can already tell the pi's cancel, right? That's pi times square root of pi is pi to the 3 halves, divided by pi to the 3 halves. So I can do a little bit of this in my head, and I can tell you that what it simplifies to. Of course we want to simplify because it just certainly makes things easier. There you go, 3 kBt over F. Okay, now, if you look at the units of this, you'll get meters squared per second squared. Remember that a velocity is a meter per second, so the average of meters squared better be meters squared per second squared. I'd like to graph it on here, but I can't. Because the x-axis is in meters per second, not meters squared per second squared. So if I'm going to plot this, I'm going to have to plot this as the square root of this value. And if I do that, it turns out to be slightly bigger. So this is b squared to the 1/2. Okay, now this is often called, you probably have heard this, a root mean square. A root mean square value. Whatever. I don't care if you remember that. Root mean square is always a little bit bigger. The average of the square root of, is always bigger than the average. That turned out to be basically universally true. I've exaggerated this curve a bit. Again, look at the textbook for real examples, but it gives you the big picture here. And if you compare that. So let me make a comparison with RMS versus average. The average, of course, is 8 kBt over pi m. You can see that what you're comparing is 3 versus 8 over pi. 8 over pi is like 2.55. So 3 is, of course, bigger than 2.55. So therefore, this is greater than the average. And so that's why I plotted it the way I did. Okay. So anyway, all right, so what? So yes, mathematically, I am capable of doing this calculation with an identity. I'm capable of plotting it on a graph. But so what? All right, now let's do an example. This might be something I do on a test. Of course, not exactly this problem. Again, I cannot emphasize enough. I will not be giving problems that we did in class, because then your strategy is just pure memorization, which is pointless. Instead, I will give you related examples where you really have to know how this works. Give me one moment. I have to wipe out the board. All right, we're back. So probably the only thing useful about doing this online is that you don't have to sit here and watch me wipe out the board. That's weird. All right, so what? Well, all right, so what that I can calculate the average versus the RMS average. So what? Okay, let me ask you this. Well, let's just do this calculation. 1/2 mv squared, right? Looks familiar. 1/2 mv average value velocity, and square that. what's that? Okay, that would be 1/2 M8 kb. So I wanted to write a pi, didn't you? 8 kb t over pi m, so that is 4 kb t over pi. Is that right? Yeah. Okay. So whatever. All right. Now let's do this. We're going to compare that to 1/2 m average value of the square. What's that? Okay, that's 1/2 m 3 kb t. I actually already forgot it, over m. Okay, so what is that? That's 3 halves kbt. Okay, so now obviously you, I'm hoping you recognize 1/2 mv squared is kinetic energy. Now both of these seem okay to me. Both are 1/2 mv squared. They both have units of joules, but they're not the same. And I'm pretty sure one of them isn't right. I mean, that has to be true. Now, which one is it? Now, I'm going to hope that you recall the class that you just took. You learned the equipartition theorem. I won't spell it all out. But that says you have 1/2 kbt of energy for every degree of freedom. I'm using lots of shorthand. Anyways, for every degree of freedom. Now, a gas molecule, given that I didn't calculate any degrees of freedom other than translation, so this is like argon. Remember, I keep talking about argon a lot because it can't vibrate or rotate. It makes it easy. Therefore, it only has 3 degrees of freedom, and so therefore, the average internal energy. Remember, the equipartition theorem tells you how much internal energy something has is 3 kbt over 2, which makes that a winner. All right, so the point is you see why there's value in calculating one versus the other. They may or may not be applicable to questions like, in this case, obviously, kinetic energy. And I'm going to throw a couple more examples at you like that. All right. The last bit I want to throw at you is, here, let me point out that, I kind of hate to do this, but I kind of need to. There's one more velocity that we can calculate, and to be honest, it's kind of more useful to simply ask you questions. It's like kind of busy work. Sorry, but I kind of need to throw this at you. So we've covered velocity, RMS velocity, but then there's another one. There's one last velocity, and then we're going to move on from this, which is most probable. Now notice it doesn't get this thing for average. It's not an average. It's a most probable. And what that is the top. Here, I'm going to redraw that thing up there, since I just seem to not want to use the board very well today. Okay, so we talked about, here's the average. RMS is to the right of that. And here is the most probable. Okay, so the most probable is the top of the curve. Now, I'm just gonna be very honest and tell you that it's just something I can ask questions on. And it is a good measure of, can you handle this stuff mathematically? And that's important. I don't want to poo-poo this too much. It's important because, I think I've said this already, maybe I haven't, but one of the key indicators of your success is your mathematical ability. And so, if I can push you a little bit in that regard, I'll do so. So, okay, how do you define the top of a curve? Hopefully you remember this. It is where the derivative of that curve, for a maximum, is where the derivative would be 0. Okay, so to calculate the most probable velocity in this example, on an exam, I'll have you calculate the most probable number of COVID patients, most probable number of cats. I will throw some kind of monkey wrench at you. And this is how you do it. Now, with that said, I can tell you that you should hope that I do that, because these are actually easier questions. All right, so let's calculate the derivative of, sorry, it's still equal to 0, but now let's calculate the derivative of the Maxwell-Boltzmann distribution. And tell you what, I'm going to throw out all of those constants. Right, remember, I keep just calling all that 4 pi m over 2 pi k dt, blah, blah, blah. I call those q. They really don't matter, just don't forget them at the end. Okay, so this is what I have to calculate the derivatives of v squared e to the blah, blah, blah. Okay, now this is going to look fearsome. But then again, I'm going to show you why this is not hard at all. Now, hopefully you also know enough calculus to know that I have this is a double function. I have a f of y and a g of y, and so what I'm doing is I'm taking the derivative of the first one and I leave the other guy alone. And then what I do is, oh, here I can actually factor that q out, right? Then what I do is I leave the first thing alone, and then I take the derivative of the other guy, which is a little unfortunate because that's going to be a little complicated. That's going to be minus 2mv over kdt. And then as usual with exponentials, they never really go away. And it's still all equal to 0. Okay, now, this looks hideous, right? So this is like, oh wait, I said a minute ago this would be the easiest problem. And that does not look like that. Oh yes it is. Oh yes it is. Boom, boom, boom. These factors cancel, right? They all cancel, they factor out. If they factor out and it's equal to 0, you can just wipe them out. So what are you left with? 2v, and now you're at the most probable. Now that you set all of this equal to 0, now you label the velocity as the most probable. And that's equal, so that means that minus sign, 2v cubed, most probable, m over kdt. And all you solve now is for the most probable. And I bet I can do this in my head. Oh, what have I done? What have I done? Did I do this right? Yeah, I did it right. So you end up with most probable squared. What did we get? You end up with over, you know what? Yeah, I forgot a 2 right there. There we go. There we go. So there's no 2. I knew something was wrong. So what you end up with is 2 kdt, 2 kdt over m square root. There you go. And sure enough, that would be less than 3 kbt. That'd be less than 3 kbt and be less than 8 over pi, which is about 2.55. Okay, so it all worked out. All right, anyway, with that said, I just wanted to point out to you that there is this one other velocity, one other type of velocity you can calculate, and you are going to see this show up a couple more times. You hopefully are looking at your homework and you see that that's there. So anyway, just wanted to point that out again. I don't know that it's very meaningful, but you can, this is a thing you can calculate, and these problems are actually some of the easier ones. So I'm actually I'm kind of working for you when I do these types of problems, so look out for that. Okay, next bit I wanted to cover was I alluded to the fact that when we are, with all this Maxwell-Boltzmann stuff, when we're learning the Boltzmann equation, which is the big picture, we narrowed down the energy to translational energy, which is 1/2 mv squared, and we've done all the things that you've seen us do with that. Actually, we can do a lot with it. That's why this is a good way to start working with the Boltzmann equation. It's one of the easiest things to do, anyway. Compared to other stuff, it's easier. Now, that's true. And you can get a lot out of it. So that's kind of, again, it's a great way to start. there's one more thing I can show you. And I mentioned this last time, that I can actually calculate the pressure of a gas. So you can tell me about an oxygen molecule, and then you can ask me what's the pressure of a mole of oxygen. And I can actually tell you. Now that calculation here I'm going to do, let me wipe out the board and we'll do that calculation. And then we don't have too much more to do. And then I'm going to go over one more example problem, and that will be most of what we do today. Just give me one moment to wipe out the board. All right, everyone, I'm back. So, as I promised, one of the neater things you can do is relate velocity to pressure. And that kind of makes sense because when you think of what is pressure, I'm thinking about that crazy gas chamber that I had popped up with some digital elements on the first lecture. What's happening is a molecule, is hitting what we perceive as pressure, whether it's some crazy gas spectrometer or just a balloon. Molecules are hitting the wall continuously. So you would think, and that's what pressure is, and you would think that the velocity at which they hit the walls would be related to pressure, which of course it is. All right, so let me show you how to do that. This is a neat little math trick, just a little algebra trick. Might put a simple question like this on the exam, not exactly this, as I've been saying. Okay, so what do you do? Okay, so let's say for one mole of gas, let's use PV equals nRT. Now the reason I'm saying we have 1 mole is I'll get rid of N. I'll just get rid of N because it's 1 mole. All right, next trick. Here's really the only trick. Multiply by Avogadro's number and then divide by Avogadro's number. Notice that I divided R by Avogadro's number. R divided by Avogadro's number is, of course, KB. So NaKBT is equal to PV. All right. Actually, we'll divide that by V, and so that's equal to pressure. Now, what we just saw a minute ago was that the average velocity is 3 kBt over m, and therefore kBt is m average velocity squared over 3. All right, so let's go back here. I know this is kind of nutty how I'm doing this. Na over V, okay, kBt is m average velocity squared over 3. And that's actually it, but let me point out one kind of neat thing. Okay, number of molecules in M, remember M is the mass of a single molecule, and I've been saying that since the beginning, so don't ever mess that up. You're going to completely screw up your homework if you forget that. Avogadro's number times the number of, the weight in kilograms of a molecule divided by the volume is the density. The density of a gas, it's kind of low, but whatever. And that's usually called rho. So therefore, the density of a gas, its average square of the velocity over 3 is equal to the pressure of the gas. Ta-da! So there you go. Interesting enough, right? Very simple relation, not hard to calculate, but most importantly, here more than any other time, I'm able to simply ask, what molecule do you have? Oh, I have O2. What's its mass? Oh, it's this. What temperature is it at? Oh, it's that. And from that, I can calculate the pressure of that gas. From the molecule, the individual molecule, to a macroscopic property, what's the pressure of this balloon? And there you go. So that's kind of the point of this class, is to do exactly this kind of stuff. Now, unfortunately, after Maxwell-Boltzmann, which we're just a few days away from, or we're getting close to getting into quantum mechanics, this is going to get harder. But today, it's not too bad at all, right? So hopefully that's the case. All right, one more thing that I'm going to throw at you, and so you have to be used to this, is we've been doing a lot with net velocity, but you may recall that at one point we derived all this using that equation that the first time you saw me write an equation across the board, which looked like this. Remember when we had the probability distribution remember how I did this? So I drew this across the board and I had e to the minus m v squared. Well, here's what I'm going to do. I am going to now do the opposite of what I did last time with Jacobians. And I'm going to take v squared, I'm going to turn it to vx squared plus vy squared plus vz squared over 2kdt. And those individual summations, which we turned to integrals, I'm now going to put those on the bottom. Vx squared over 2kdt. Remember when I did this? Okay, so I'm going to speed things up here because why wouldn't I? Okay, so there you go. Now, what can I do with this? So, recall last time that one of the first things that, the first time we started talking about using identities and whatnot, that this turned into m over, sorry, this is actually 2 pi kbt over m to the 1/2, and all of these are exactly the same. And therefore, what this turns into is we can now turn this into a triple integral, which actually, let me give myself some room. Here, let me write that right here. Okay, what does that look like if I do that? What's the point? Okay, let me write all this down. Sorry, folks. I know that's I said last time that I'll try to not do this kind of stuff because we can write things together, but it's just mind-blowing. It takes a long time to write all this down, and it's still, though, you should be writing it down too, right? Okay, so I've taken our Maxwell-Boltzmann distribution, and you can see why, at first, I wanted to do things in net velocity, because this is kind of hideous. But it's not that bad, right? Because it's really just the same term multiplied by itself 3 times. It doesn't really matter whether it's an x, y, or z. So what's the point then? What can you do with this? Well, you can ask yourself a neat question. Start asking some really neat questions that you know the answers to. And so when I ask you stuff like this on an exam or on homeworks, what's good about them is you know what the answer is going to be. You just have to prove it. And you may have noticed that in the homeworks, that I like to provide answers to the problem. Sometimes I'll just tell you the answer. Sometimes I hide the answers to problems and other problems. And that's because, for one, it's funny. Number 2, I don't want you working with no guidance at all, because we're really separated, right? And the more I can kind of be present when you're doing your homework by, to be blunt, providing an answer, in honesty, it's helpful. Obviously, it's helpful. But you still got to get it right. Okay, so anyway, so what's the question? The question for which this is going to help. How many molecules are moving up? Huh? Oh, come on, that's pretty plain spoken English, right? But now you just got to mathematically interpret it. By how many molecules, let's say we have a mole, and therefore what percent of that mole is moving up? All right, well, I would imagine that anything is equally probable to be moving left, right, up, down, or side to side. So I'm going to go ahead and assume that for any molecule, if I can grab a molecule right in front of me, and it's moving in any direction it wants, it's 50-50 whether that vector is up versus down. Okay, so you see, you know the answer. This is actually kind of like it's kind of like a childish question. Where it's not childish is now you have to use this to prove it. Now the point of this is that now you have to understand what this damn thing does. Now remember, we're not doing average value, this or that. This is just the Maxwell-Boltzmann probability distribution. So I know that when I integrate this thing, this triple integral, over all possible values, and remember that these are directional, so therefore they can have negative velocities. Vx can be negative, Vy can be negative, Vz can be negative. When I do this, I'm going to get the number 1. Actually, each one of these is 1. 1 times 1 times 1. You can double check it. I think you can, look online for an identity. I think I have identities in the homework. Every one of these is 1. So 1 cubed is 1. All right, now that hopefully is a clue to how to do this problem. What fraction of molecules are moving up? Okay, well, up is not x or y, but it is z. Now, a molecule moving up, what do I change about this? Now, this is 1, this is 1. And I already told you the answer. This has to be half. How would I turn an integral? So let's think about this several ways. How would I turn this integral, which is 1, how would I integrate, how do I make that half? Well, I bet I simply take the limit and halve it. So instead of going from minus infinity to infinity, I'll go from 0 to infinity. Okay, so that, you look up the identity, and it's a half. So now you got 1 times 1 times a half. You got the right answer. But now, part B of the question is, but why does it make sense? It makes sense because I'm asking that the probability has a positive velocity in the z direction, right? And that means it's moving up. So there you go. Again, look up the identities. This is 1 times 1 half. And that means it's a half, which is equal to 50%. So that's how you answer that question. I will ask similar questions to that, and so look out for that. That's really not too hard. Okay, now before I end, let me give you a challenge question. I'm not going to answer it. I'll actually do this on Friday. Now that you've got a handle on this, and let me show you one other type of question I can do with Vx, Vy, Vz. Let me throw this at you and you see if you can figure it out. What is, so this is not related, what is the average velocity in the x direction? What would that be? Okay. I think you can answer that question, but now let me do another one. Let's do the average velocity in the x direction. For molecules moving forward. Okay, so 2 challenge questions. I'll answer them on Friday. But for those of you who, you A-types, pre-mids, try it. Now, I think I've given you more than enough to do this. You're simply going to work with this part of the 3D Maxwell-Boltzmann equation. These you can keep, but they would integrate to 1. Now, when it comes to the same question, this is like an offset of that. For molecules only moving forward, again, hopefully you see what you have to adjust in your little one-dimensional Maxwell-Boltzmann equation to answer that question. Now, I'm not going to answer that right now because we're out of time, but I will answer it on Friday, so I'm not going to leave you hanging. And you may have a question like that on exam, so it's worth trying to figure it out on your own. So anyway, with that, I have no idea what time it is. No idea. That's one of the best things about doing this. Hopefully that we're ending on time or it's a little early. Regardless, one more lecture on Maxwell-Boltzmann and we are done with this and we move on to quantum mechanics.